Good morning. In our previous class, we have started discussing about the zones of porous media, where we looked at the different zones briefly per se, just reviewing some basic concepts that affect the porous media. We looked at the unsaturated zone, the capillary fringe, and then the saturated zone, where we define certain terms that affect these zones. And one of them is the moisture content, the porosity, the saturation. All these terms tell us in one way or the other about the amount of moisture that is present. Amount of moisture down to the amount of water present, depending on whether you are talking about the saturated or unsaturated zone. And today we'll continue with aquifers, where we will define the different types of aquifers, which you all know, and then we'll move a little bit, not deeper, but still talk about the properties of aquifers. A lot of you, like I said, you see this is our third lecture, but yet we are still on the very, very surface. But all these superficial topics and processes that we are discussing are very instrumental when modeling any groundwater process. Because one thing we'll realize is that in a model you have input, process, output, isn't it? All these parameters, these properties will serve as input into the system. And once they will serve as input, it means they will in one way or the other affect the modeling process. So you have to understand every input into your model very well. How do you determine it? How do you find it, if it's analytical or empirical? What is it in the first place? And how does it affect your system? So that is why we are starting from the very basis, in the sense that even for someone that has never studied hydrology before, he won't find it difficult to catch up with what we are doing, given the pace at which we are moving. Okay? We held a concept quiz where you were asked to derive the mathematical relationship for the following variables: moisture content due to water, due to air, and porosity. Okay? Because we define porosity as a measure of the void within the porous media, within the solid matrix. Okay? We mentioned that you have the solid matrix and you have void space, and this void space can be filled by air, water, or pollutants, as the case may be. Okay, so porosity is a measure of the void space with respect to the total volume. So it's the volume of the void over the volume of the soil matrix. Okay, in which the moisture content, on the other hand, is a measure of how much water do you have with respect to the total volume, and with respect to air, how much air do you have with respect to the total volume. And we have mentioned that more often than not, we have water and air filling the void space. So meaning this theta W plus theta A will add up to give us the porosity. Okay, this was the theta W plus theta A will add up to give us the porosity. Okay, well, that is with the assumption that the void space contains only water and air. Like I said, it can contain other things in case of pollution, isn't it? So you will have other things in the void space. But with the assumption that you have only water and air, then theta W plus theta A will add up to give us the porosity. Okay? This we did, like I said, some got it right, but some were thinking it's one complex mathematical derivation that they need to do. And that's why I call it concept quiz. I have explained the different types of quizzes that we are going to have in this class, right? There's the reading quiz, which normally we may not have, just to read, to energize you, to introduce a particular topic, to see how much of the topic you know. That's the reading quiz. And then you have the attention quiz, just part of what we discuss, and then to see how attentive are you at following with our discussion. Just simple things that can come up. And then we have the concept quiz. The concept quiz also is part of what we will be discussing in class, but it tests your ability to understand the basic concepts, understanding of the basic concepts. So that's what the concept quiz will be asking you about. Yeah, sometimes it will be like a classwork just to do it, and I will go around. Sometimes I can ask you to write your number and I will take it home to go and grade. Okay? And then there could be a whole quiz or a test and what have you. All what it means is that while in class, you have to be very attentive, and you have to understand all the concepts that are being discussed, so that when such concept quiz crop in, you will be able to quickly, put the right answer on the paper. Okay? So, having discussed the different zones in the porous media, today we are going to move to aquifers, and hopefully we'll finish with the different types of aquifers, and then we move to the properties of aquifers, which is the most important thing. Okay? As for the aquifers, we know the aquifers, they belong to the saturated zone, isn't it? Because they are the underground reservoirs that we have that hold the water that we need to pump out or do whatever that we want to do with them. And we have a saturated geologic formation that can store and transmit water to wells at economic rates under ordinary field conditions. This is like the perfect definition of an aquifer. Okay? It is a geologic formation that can store and transmit water to wells at economic rates under ordinary field conditions, meaning under gravity, without the need of either introducing any artificial thing to push it here or there. Okay? It stores water, it holds it like a reservoir, and then it transmits. When you dig a well, it will now go, inside your well under gravity, and at economic rates, at rates that it will be useful to you. Not that you dig a borehole and the yield is not appreciable. At economic rates. You see, that is why when we talk about oil, you will hear them saying that, okay, this region has oil, but not at economic rate. It means there is oil, but it's not worth exploring, because the amount of money to be sunk in the exploration and what have you, the geologic survey and all that, only to go and realize that the amount of oil present is just, very small few liters or barrels. So that's why they will now tell you, no, here it has oil, but not at economic rates. So meaning it's not worth exploring at all. So the same thing with the aquifer, it has to be able to furnish water at economic rates under ordinary field conditions. This is what we know. There is nothing new here. And the types of aquifers, example, we have limestone aquifers, sandstone aquifers. Sandstone, not sandstone. I don't know, maybe sandstorm has terrorized me a lot. Here we don't usually have sandstorm, isn't it? So you don't know what sandstorm is.
I experienced it even when I was serving in Sokoto.
In Sokoto, okay, near the desert. Sokoto, Maiduguri, once in a while probably you will experience, and those in Niger, I suppose.
So,
isn't it?
Those that came from South, they are very scared. Guys are going back home like,
no, sandstorm is more terrible than whatever you can imagine. Sometimes more terrible than, heavy downpour of rain, because you can't see anything. All your houses can be filled up. Your visibility becomes very small, and it's really terrifying. So maybe it has terrorized me so much that I am even calling sandstone as sandstorm. So don't mind me. It is sandstone, not sandstorm. The horizontal extent of an aquifer is much larger than its thickness. This has some modeling implication. The horizontal extent is much larger than its thickness. The thickness B, which we normally call B, is usually extremely smaller than the horizontal extent, than its length. Okay? This could have some implication when we come to the modeling aspect. Okay? And always think of an aquifer as a thin layer, meaning the depth, the width of the aquifer is usually very small compared to the length. Okay, so always think of an aquifer as a thin layer. Okay, although of course it may be the volume can be great, but when compared to the length, it is nothing. The width is nothing, because we have transboundary aquifers. An aquifer that transcends, let's say, from Nigeria to Niger, and even passing Niger to other countries. So you can imagine the length. Do you understand? And then other geological formations, which are not called aquifers, because aquifer must store water, transmit water at economic rates. Even if you have a geologic formation that stores water, but it's not transmitting at economic rates, you don't call it an aquifer. It has a different name. Then that takes us to aquitard. Aquitard, e.g. sandy, clay, it stores water, but does not transmit under ordinary field conditions. So for that, it has violated one of the basic characteristics of an aquifer, which is the transmission. Okay, so that's why it is called an aquitard, such as sandy clay, may leak water vertically to adjacent aquifers. Because normally, as we are going to see, aquitards are usually like the separating structure or geologic formation between adjacent aquifers. But it may leak water vertically to adjacent, but that is not appreciable enough. And for modeling purposes, we will consider aquitards as no flow boundary. Although now you may not really get what is meant by no flow boundary, but even as that implies, no flow, meaning no flow in or out, isn't it? So zero flow. And for that, we'll do some boundary conditions and then we move on. But that is when we will move, when we finally reach the modeling proper. And that's why, like I said, here we will look at the properties, most especially those that will affect our modeling aspect. So here we'll just mention, okay, no, where is it? May leak vertically and it has negligible flow. But when we go to the modeling, I will just mention, okay, this is an aquitard, as we have already mentioned. So this is a no flow boundary. Okay? And then we have aquiclude or aquifuge, which example you have unweathered fractured granites and carbonates. They can also store water, but normally their fissures are not connected. So they have water, but not readily transmitting such water to wells. And their porosity may be, they may not have a lot of fissures, although they could have, but unconnected fissures, carbonates and granites. So that make them bad aquifers, or in another word, aquiclude, because they exclude the water. They now isolate the water. You remember when talking about the porosity in the last class, I was introducing something called effective porosity, isn't it? I told you about the total porosity and effective porosity. In the next slide, or no, not next slide, next presentation, which I hope we are going to start it today, we will explain more about the effective and the total porosity, because porosity is the measure of the amount of voids. I mentioned that those voids or interstices can be connected or unconnected. Those connected are called effective, constitute the effective porosity, because that is the one we are interested in groundwater. We are interested in the groundwater flow, not the water that is being isolated from the system. So for that reason, we will be dealing with the effective porosity. Okay, and then we will also discuss how do you determine the effective porosity under lab condition and what have you. Okay, but that does tell you that granites, carbonates, they can have water, but usually the interstices are not connected. So as such, they will constitute bad aquifers or aquifuge or aquiclude. Okay, and for all practical purposes, an aquiclude may be considered as an impervious layer. And this also has modeling implication. Okay? When you have an aquitard or an aquifuge or aquiclude, you can consider it as an impervious layer, same thing as the no flow boundary. Okay? And then they play a role in formulating boundary conditions. I just finished explaining. Okay? All these different types of aquifers, they play a role in formulating boundary conditions, because if you have an aquifer, it means in that case there is flow. It is not a no flow boundary. Okay, but any other one, aquitard, there are no flow boundaries. So they help us in formulating boundary conditions. Okay? Now, this is the common figure that we normally have, of the section through the soil. From Todd, I think the picture first came from Todd, the popular book in groundwater, where you have the ground surface and then you have all the different aquifers. We have a perched aquifer. Perched aquifer is more or less like detached from the main. It is usually found in the unconfined aquifer, the unconfined zone. Okay, so it has certain depression that it can hold water. Let's say if you sink your well into it, you will get water, but that will be really temporary because it doesn't have large aerial extent. The amount of water will be very limited, isn't it? So it is called perched aquifer. Okay, you only have like an impervious layer, an aquitard, and then it has certain depression that the water can stay there. Okay, and then you have the aquifer A, B, C. Aquifer A is the unconfined aquifer, as we all know, isn't it? Which is the one before this impervious layer. Okay? This is the impervious stratum, which can be aquitard or aquifuge, isn't it? Usually made up of clay and silt or silt. Like I said, clay has high porosity. Clay has high porosity. But we are going to, when we start defining terms affecting aquifers, it has very low yield. The specific retention could be high, but the yield extremely low. Okay? So you have an impervious layer, and then you have another aquifer B, which is now confined. By the time confined, it means it has upper and lower boundary, confined by an impervious stratum. Okay? Like in this case, it is bounded above and beneath by an impervious layer of aquitard or aquifuge. Okay? And then you have water, and then you have another aquifer C. Can you see that? So B and C are what? Which one? Confined aquifers. And A is what? Unconfined, isn't it? So when you dig your well to hit aquifer A, you see it hits the unconfined aquifer. Okay? So after so many years of withdrawal, the water table could be affected, and you may find that no water is flowing into your well. Okay? But when you hit, and you can see each one has a source of recharge. Can you see that? This is the outcrop, where the source of water is actually coming from. Okay? This is where this, because we are assuming that no water is going from the unconfined to the confined aquifer, although, like I mentioned, there could be some small leaks, isn't it? But for practical purposes, we are assuming that no water, the two waters are not connected. Okay? But this is the source. If you trace it, you will find that there is an outcrop somewhere. Okay? And this can go as far as it takes, transcending from one country to the other. That's why, like we said, the thickness is so small compared to the length. Okay? And also, this aquifer B can be different from aquifer C due to the material, the particular geologic formation. Is it sandstone? Is it limestone? Is it granite? That will what determine whether it is a good one or a bad one. Though confined, because this can be made up of, let's say, gravel, which constitutes one of the base aquifers that we have. Gravel, sandstone. Sandstone. Okay? So all these constitute some of the best aquifers that we have, which stores good amount of water and transmit same at economic rates. Okay? So I mentioned the recharge. This is the groundwater. Now, again, looking at this figure, we can add some things in the sense that, you see, the water in the unconfined aquifer is not under pressure. It's not under pressure. It's not under pressure. Once you sink a well into it, the water level gives the phreatic surface or the water table of the unconfined aquifer. But the water in the confined aquifer is under pressure. It's just like a flowing water in a pipe. When you put a tap or when you punch it, it goes up because it has, the pressure head is high, isn't it? While for unconfined aquifer, it is not like that. But for confined aquifer, it's much more similar to flow in pipes, which is under pressure. So in that case, when you have a well that now penetrates into a confined aquifer, the water level definitely will be up to the phreatic surface or the piezometric surface. And in that case, depending on the point where your well is, you can have an artesian well, artesian pressure well, which can be flowing without even pumping. If the piezometric surface is above the top, the surface of the well. Look at this well. Can you see that? Can you see the water level? The water level at the recharge area is this, isn't it? So the piezometric surface will follow this, isn't it? So if you sink a well through this aquifer, you can see the top of the well is below the piezometric surface. So it will constitute an artesian well. And you have such wells in some areas, even in Maiduguri. You can have an artesian well. And this is the hydraulics behind it. Okay? Because the piezometric surface is higher than the surface of the well. So it will flow under pressure. I mean, without the need to pump anything. Unless, of course, the water level goes down below the surface of the well. Okay? But let me not presuppose. If I want to pump water from two levels, I want to pump to this level A. Not pump, but by gravity. If my tank is this, can it come to this level? No?
With gravity?
Yeah, under gravity. Maybe the tank, my pipe, like this.
No.
All of you know? Why will it come?
It has the same level.
Let me say this is the level. Okay, let's assume it has the same level.
It will go
Under gravity.
gravity, yes.
So it depends.
Okay, go ahead. Quick, because today, we have just 1 hour.
It depends upon
And the interaction session has already started. So quickly tell me the answer so that we move on. Yeah.
depend upon the volume of the tank.
The volume of the tank. Which pressure is under gravity? It just contains
The
water.
volume of the tank. So the head.
So
So what are you saying? What will be the implication of the losses on the delivery?
the head will reduce, so it will be to the level of A. The water will reach A.
It won't reach it, although it is at the same level.
Right.
Volume reach.
The water cannot reach it
Why?
because the water is flowing by gravity, because the gravitational effect as the water goes down from the tank, because the tank and the A are at the same level. So the water can only reach the level below the level of the water in the tank.
Below the level of the water in the tank?
Yes.
It can only reach this point?
Below the level of water in the tank. For instance,
Like this level? Are you talking about this
for
level?
instance now, the water is at maybe
Are you this level?
It's at the top. Let the tank is feed.
I told you we'll be going down to basis, isn't it?
Yes.
This is fluid mechanics. I mean, probably.
The tank is feed.
Okay, maybe 501. Let me say 501. Let me go as high as 501.
The water can be above B if the water is maybe let's say the tank is feed.
The tank, yeah, filled to capacity.
Yes, it can be
Filled to
above-
capacity.
It can be above B, but it cannot reach it.
Above B.
Yes, it can flow above B.
It can or it will.
It will flow above B, but it cannot occupy the tank at A.
So it cannot come here. Why?
Because there's not going to be enough energy for the water to move to occupy a tank at B.
Where will the energy go?
Because it's flowing at
If I put a piezometer here,
yes.
where do you expect the water level to be? Are you following?
Yes.
If I put a piezometer here at the bottom, where do you think the water level will be in that piezometer?
At the surface level.
At the surface level.
Top?
Exactly.
Exactly at the level of where the water in the tank is? Someone wants to say something?
I say the water will be try to maintain its level. The water in the reservoir and the one in the
Hmm?
will try to maintain their level.
Yes.
Here?
But it's not
The water in the reservoir and one in the
yes,
pipe.
one by the reservoir at the top.
This one? This
It can fill up.
so if it is filled to this, so it will be up to this level?
Yes.
So it depends upon the volume of the tank.
What about the concern raised by this guy? What's your name? Shamsuddin.
And that is why I say, he said best of the head, the water will try to maintain its
Okay, now let's say this morning I took food, let's say a balanced diet, or let's say a high calorie food. What is a high calorie food? Let's say fat, protein, which gave me an energy of let's say 100 kilojoule. Okay, and I want to run from here to the gym. What do you think of this energy that I took? What will become of it? Will it remain the same when I get there? Why? I have used some to.
You lost some energy.
So why are you not applying the same thing here? How did you forget all about the losses? When water flows in pipes, you encounter losses due to a lot of things, due to the size, due to at bends, friction. Even if there are no bends, as it is flowing, there is friction between the water and the pipe, which is in a way retarding or making it to lose energy. And that energy is in form of, oh, we are going to energy now. Thank God. So, which will now affect the pressure. The pressure head, isn't it? Because here we're only talking about the pressure head, right? So, of course, it will not come to this level. Even if it is filled to capacity, of course. No two ways about that. But why is it so? Because there will be losses. There will be losses as it flows. But probably if you just put a piezometer here, it could rise up to, because it's a very small diameter, so even under capillarity, it can rise. Even depending on the size, it can even rise above, depending on the capillarity of the tube, the size of the tube. Okay? Why am I going down to this basic? Because it affects us here. Okay? We are talking about artesian well, okay, which flows under pressure. I was mentioning that if there is, probably if the piezometric head for overdraft or what have you drops down below the surface of the well, like up to this level, then this well, the water level will be up to this, isn't it? Now this one, Aquifer C, when you sink a well, it will be up to the piezometric head or the piezometric surface. What is piezometric surface or piezometric head? Water table? How do you define it mathematically?
Gravity.
How do you define it mathematically? Piezometric height of the? Yeah, the water level. In this case, this is the water level in this aquifer. But this is the piezometric head.
Height of water table due to
Mathematically, how do you define it? What other? Because you are talking like a layman. I want you to talk more like water engineers now.
The difference between the water table, the slope of the water table.
The difference between?
No, the level over there and the one over here is.
I don't know which one over here and over there.
But the one by the left.
Left.
Yes. Let's say
there are two levels here.
Level at the center. You want to take the physiometric head at the center. As you can see, you have difference in height, which is the head.
But here we have different aquifers.
No, assuming we are considering the one at the center.
Which one aquifer? A, B, or C?
C, for instance.
C, this one.
Yes. So you can see the reference point. Then you consider the water level.
Can you come out, please? Because I don't understand this. Probably if you show me, then it will make more sense to me.
What I'm trying to say is this.
Yeah.
The level here and here.
Where?
So here.
Here?
Yes. The
And
water
here?
level here and here.
Okay.
So you expect a difference of height due to gravity.
So
So it will increase the height of
I think you came late. Did you come late?
No, I'm coming to this.
No, I mean you came late to this class today.
Yeah.
Oh, no wonder. Did we start explaining this with you? Or you just came while we started?
I came when it started.
Oh, no wonder. Okay. And that's why it's very important to come early, isn't it? You should come before we start so that you don't miss anything. If you remember, I started explaining the different types of aquifers depending on the height, isn't it? Or depending on the presence of an impervious confining layer above or below. Okay? Where we define two types or three types. Perched aquifer, which is more or less like temporary in the unsaturated zone. And then we have the unconfined aquifer, bounded only below. And then we have the confined aquifer, which is bounded above and below. And then we talked about the impervious layer separating the confined and unconfined, which is the impervious stratum, usually an aquitard or aquiclude. And I said what? The two are separated. Their hydraulics are different. And probably even the water quality in the aquifers are different. So now that you are trying to relate this with this, so that's why I said, okay, this with this, the water level here has nothing to do with the water level here. Aquifers, like I said, they have point of recharge area. So depending on the water level at the recharge area, that will determine the piezometric head.
That's what I'm trying to say.
But has nothing to do with the water table here, which is for the unconfined aquifer. This one affects only the unconfined aquifer. Simple. Did you get my point? The water in the confined aquifer is almost inexhaustible, unlike the water in the confined aquifer, which is usually affected as a result of overdraft. Sinking wells here, pumping, the water level will keep on going down. But that of the unconfined aquifer, even the pressure remains virtually the same because it's a reservoir. It has large aerial extent. And then we are going to define some things that affect aquifer and that makes the water volume to almost remain the same, or the pressure head to remain the same. We are going to define stresses acting, total stress, effective stress, and the pressure. This we are going to do, I think, in the next slide or the next few slides. So the water in the confined aquifer, the pressure remains the same over time, unaffected, despite the fact that you are continuously pumping. But it is considered as more or less inexhaustible reservoir. And how does it adjust itself despite the fact that you are still pumping from the aquifer, but the pressure head remains the same? How does that happen? Like I said, we'll explain using the total stress, effective stress, and the pressure, and the compressibility of water. That will take us to the compressibility of water. Probably we'll discuss that in the next presentation, which will be when discussing about the aquifer properties. All this basic, because this figure, you have seen it right from, I think, 401, isn't it? And then 503, and then the master's hydrology and what have you. But now we are looking at it from some other perspective, of course from the basis, and then highlighting certain important features that is going to affect our groundwater modeling system. Because like I said, modeling is, before you can model something, you have to understand everything that affects it. And when I say understand, it doesn't mean just maybe memorizing the definition, memorizing the mathematical expressions, no. But having like a feel of exactly what it means or what it is. That is the only way that our modeling can have a smooth sail. If not, like I said, when I come to the class, we can just go to the governing equations, boundary conditions, and then apply whichever solver to use and get our result, and then call it a day. But in that case, you won't gain anything. But this way you will, once we start the modeling proper, all this background, all these basic processes will be very clear in your brain. And then the modeling will have easy flow. Okay? Now, I think I have said most of what I want to say about the confined and unconfined aquifer. And this is one of the types of aquifers. That is based on the presence of an impervious strata or stratum. Okay? When bounded from below, you call it unconfined, which has level equal to the water table, isn't it? And then you have, and the water is not under pressure. Okay, it's not under pressure. And you have the unconfined, which is bounded from below and above by an impervious or semi-impervious stratum, isn't it? And then which is under pressure. Pardon? The confined, yeah, which is under pressure. And whose volume is almost inexhaustible. And that's why more often than not, from this now you can, when you talk with people on the street, that they say, oh, I have borehole, but now the yield is almost zero. Despite the fact that I dug the well, to, let's say, 30 meters around Zaria, usually 30 meters, you can find appreciable amount of water. When your well, be it borehole or whatever it is dug into an unconfined aquifer, it means the water table fluctuates. The yield also fluctuates, depending on season and other surrounding wells that may be extracting from the same aquifer or from the same unconfined layer, isn't it? But when you hit a good aquifer, then it will be sustainable. The water, the yield from that aquifer will be sustainable over time. It will be unaffected by season or by the amount of wells tapping from the same aquifer. The yield will remain the same throughout. No complaint about, no, now I just dug this well for like 2 years and now there is no water again. And that means probably before sinking any borehole, you should have geological survey of the area. When you have geological survey, you all know how to do that, isn't it? By sending some sound signals, and then depending on the geologic formation, it makes certain sounds, which will now translate into the particular geologic formation, and even the amount of water present in that aquifer. And sometimes they can drill some. They can do some drill to extract exactly the material, the geological formation at various levels, using well log, isn't it? So if you can have something like this and you can like demarcate exactly, okay, this is the unconfined, this is the unconfined, and the confined is a good aquifer, and you will know the level, at which level, So you quickly sink your well up to that level and you are done. And that's exactly what happens even when you have oil, when you are prospecting for oil. Because oil usually is beneath water. Or sometimes you can find it above it, but usually at much, at greater depths. But the same geological survey that you do for water is the same thing you do for oil when undertaking any oil prospecting, investigation. You do the same thing. And that's why I don't know for this if our country is completely mapped. I doubt, because that is why still we are finding oil now. I think in Sokoto, the Sokoto basin, they confirmed there is appreciable amount of oil, but they want to do all the modeling, the reservoir modeling before they start prospecting. And the same thing in the Chad basin and also somewhere in Bauchi. But that tells us the whole country needs to be mapped geologically. To have a map, to have a clearly defined all the aquifers and what have you. Okay, this one, does it contain oil or is it good for water? And that will aid in water prospecting and also oil exploration. Saudi Arabia, the whole country is mapped. So they know exactly where oil is, where gas is. And that will help also the geologists and the water engineers in the sense that, okay, this aquifer has so much amount of water. And this one, no, it's a bad one because of the material is clearly defined. And that takes us to another question, which I was supposed to have done it here. Oh, why does it start from the beginning? Yeah, I was supposed to have done it here. We talked about the sustainability of groundwater with respect to surface water, isn't it? So, what in your opinion, with respect to the sustainability of either surface water or groundwater? Here, I know we are used to having, the surface water as for municipal water supply, isn't it? Do you think we can use groundwater the same way? Is it sustainable enough? Is it reliable enough that we can use groundwater and pump to our treatment plants much the same way as we do with the surface water?
It is sustainable, but reliability is the problem because we have this power problem.
We will discuss this for the next 5 minutes. So when you want to present your point, do that as fast as possible. Like I said, today I have just 1 hour.
Because of the power problem we have, the reliability might be shaken into, but in terms of sustainability.
How does power affect the reliability of groundwater? In what way?
A place where groundwater is being proposed to use for municipal water supply, place in Castina, they sink the well, put a storage tank in place, then later transfer that same water to another overhead tank. But the problem is that power failure in that particular place is so pronounced, and they will need to add to it in terms of economic aspect, need to put in place maybe another source of power, like a generator.
How will it differ from surface water? In the same place, the same case study. If we are using surface water, how will the power problem, how is the power not going to affect if it were a surface water source?
Mostly surface water, the means of conveyance is mostly via gravity.
Mostly via gravity?
Yes.
Means of conveyance?
Yes.
From the
Because they will have,
probably you.
after the have been put in place, they will only use
You are not in environmental, so maybe I could have asked you, haven't you done water supply? There is a course, I think water supply, whatever, and treatment for those in environmental. So you normally have but even though you haven't done it, you must have done, I think, Rem 505, isn't it? Unit operations, yeah, 507, right? Where you talk about intake structure. Even for the surface water, you have an intake structure. And the intake structure, is it always by gravity or you pump it? So, you will still need, it's only when you have hydropower, when you talk about REM 502, what is it called? I forgot. I know it's hydropower. When you have penstocks, that is where the water flows by gravity to the penstock, isn't it? So that it turns, the turbines, and then water is generated. You have the head water, the tail water, and then if you want to reuse the water, you have to pump it back to the head water reservoir. But as far as the treatment plant is concerned, that is not always the case, that it must always be by gravity. Okay? Now, any other idea? Can we use it or not? Let's say for Zaria, can we sink some boreholes, and then the same way we have treatment plant where we have surface water as the source, can we pump water from our boreholes to the treatment plant, and then it will suffice the whole of Zaria town? Do you have this idea before coming to this class, or it is now after this explanation that you now have this idea?
I really have not looked at it like that.
Before?
Yes.
Before now?
Yes.
Okay.
But considering the fact that water always sinks down, we have less losses on the ground compared to at the surface. So yes, it's inexhaustible. So I think it's more reliable than even the surface water.
Any other view? So do we all accept that we can use it for municipal water supply? No objection.
Excuse me, sir. I think it should be discouraged unless necessary.
Why discouraged?
Yeah, I think it's. I am not sure, but from my own perspective, emptying the water table.
What? Empty?
Let's say we are pumping it at a very high rate. It creates a kind of vacuum, of which I don't know if it's going to be chaos later. I don't know. I'm not sure. But I don't think even that vacuum is kind of a good idea. But I've seen places where groundwater is very charged. Places like Yobe and other places. But I'm not sure.
It's possible, but it will be costly.
Exactly.
It will be costlier than surface water?
Yes, sir. Yes,
Did you attend our last class?
yes, sir.
Oh. Oh. You should be consistent. You should be coming to class every class session you should be there so that you don't miss anything, isn't it? And when coming to class, you should come as early as possible so that you don't miss a word, isn't it?
Please, I have this question. The energy that will be used in extracting water from groundwater and that of pumping, I think pumping from the normal to the surface reservoir, I think it will differ. Considering the energy required to pump out.
Yeah, but when we look at the overall picture, okay, let me go to your first comment about the adverse effect it could have on the subsurface, in the aquifer, because of overdraft, so there could be, the water is going to reduce. But I was just telling you that the water in the confined aquifer is inexhaustible. But still your point has some validity in some respect, because there is what is called subsidence. You must have done it probably in the soil mechanics and what have you. That is what is called subsidence. pumping so much sometimes, I mentioned that it doesn't affect the arrangement of the grains, of the porous media, of the soil matrix, because of some a process that we are going to explain about the total stress, while the water remains the same and the grains also almost intact due to the compressibility of water. But still, sometimes in few occasions you may have what is called subsidence. There may be some slight depression as a result of pumping. But this is an exception rather than the rule. So when pumping water, we don't even put that into consideration at all. But still, it exists here and there. Minimal amount or negligible amount. Now talking about the cost, the power cost. You don't just look at the power cost, because the ground reservoir, you don't create anything. You don't dump it, isn't it? No dam created. You only sink a well to touch whichever aquifer that you are interested in, isn't it? So the cost will just be drilling borehole, or let's say, drilling borehole into the particular aquifer of interest, and then putting your pump, right? And that's it. But then for the surface water, the first thing you have is dam, isn't it? Which is usually, because you have different types of river streams, you need to have a perennial stream that flows throughout, a perennial river or what have you. Which one is usually far away from the town, from the city, far away, more often than not. And then you dam it at a particular appropriate place, not near, a lot of considerations, which will take it farther away from the city. And that will increase the cost for pumping, ultimately. And then when you dam, the cost of dam, I will leave that. You must have done dam and reservoir operations. Or you will do it if you haven't done that, for those in MSc 1. So the cost of constructing a dam is really humongous. The maintenance, and then the power requirement, the intake structure, and then the pumping. So you don't just look at power cost in isolation. You look at the cost in totality, the overall cost, when considering either surface water as your source or groundwater. And then coming down to the treatment, because more often than not, surface water, its pollution rate is higher than groundwater. Yes, we can use groundwater as our source for municipal water supply. But unfortunately, I don't know, here in Nigeria, I don't know any big town that is using groundwater as its source of water. I haven't yet studied so much the geologic formations that we have in Nigeria, but I know definitely that we can have good aquifers that are reliable. When I say aquifer, I'm referring to confined aquifers, because they are the ones that are more sustainable in the long run. The unconfined, it varies over time, over season, and depending on the amount of abstractions taking place, isn't it? So I'm not talking, when I say source, I'm referring to the confined aquifer. Of course, maybe when you go to geology, I'm sure they could have, let's say, probably the geologic mapping of Zaria, and maybe something like that table that we have, something like this figure. Something like this figure. Probably they have that of Zaria, and whether this is good, this is that, and the amount of water that could. If we have this, then it only takes planning. You can sink your wells, let's say 15 wells, 12 wells, and it may as well replace the surface water source.
So our fear is this.
Do you understand?
We only have fear because our maintenance culture is poor.
Our what?
Maintenance culture is poor.
Maintenance, in whichever case, your maintenance culture will affect the source of water, even for surface water.
Surface water.
It doesn't make it less, as in the case of groundwater. It doesn't make it less.
It's not that it's less, but sometimes when even when you didn't maintain the the surface water system, you can still continue to produce and get a reasonable, appreciable amount of water.
How so?
Because
what is the maintenance that is needed for groundwater source? Tell me.
For instance,
what is the maintenance?
If you seek a borehole, one, for instance, sometimes you need to change. People are not ready to be.
Change what?
Maybe filters.
Which filter?
Changing.
We are looking at now groundwater for municipal water supply to pump to the treatment plant, and then it undergoes probably, depending on the water quality, maybe filtration, disinfection, or sometimes probably coagulation. We are looking at groundwater in that respect.
I think another is
the quality is public.
That as I said, pollution is also possible to have pollution in groundwater.
Yes.
Now, should such a thing happen, for you to correct it, I think it's not going to be the same way when you have such problem of pollution in surface water supply.
And that is why even the water quality in the aquifer, within the same aquifer, could vary spatially. When I say spatially, meaning over distance. Okay? And even from the geologic survey, it will tell you about the quality. So you go to a place where the water quality is high. Like I said, aquifers transcends countries. You have transboundary aquifer. You know, our problem here is just the fact that we are not disposed to using groundwater for municipal water supply. Even where we do it, because, you know, politicians, more often than not, sink boreholes here and there, use solar as source of power and what have you, isn't it? But then still, after a few months, a year or two, the same borehole, you go and realize that it's not working, isn't it? Then what is happening? It's about the planning. It all boils down to planning. Saudi Arabia has its water need, water demand is much higher than what we have. Although the population is nothing to write home about, just 33 million. We are now approaching 200 million. Yeah, we are approaching 200 million. But the water need over there is maybe much higher than what we have. The water need is about 2 billion liters per day. The water demand. And half of its water demand is satisfied by groundwater sources. Half, meaning 1 billion liters per day, is from groundwater sources. The other half is from desalination. Seawater desalination. Because it is bounded usually, you know, by you have the Red Sea from, you know, this area, and you have the Arabian Gulf from the other area. So it has the largest desalination plant in the world. And you know, desalinating water is the most expensive water treatment process. But what option has it got? There is no river in Saudi Arabia throughout. It's all desert. No single river. No single river. It's all desert. But it has the largest desalination plants. So 1 billion liters per day is supplied by by groundwater. The other 50% by desalination plants. So you can have a whole town, the town where I lived, is supplied by about 15 wells. No even water from the desalination plant. Completely relying on groundwater sources. 15 wells, which were situated around 100 kilometers away from the town. And then they pump to the treatment plant. Then it undergoes treatment. It supplies that town and even neighboring towns. So groundwater is highly reliable. And don't forget, we still talk about the amount, isn't it? We talked about the amount. How much water do we have? Yes. Groundwater, we have 0.61% globally. Surface water, 0.009%. And when I asked you to take the percentage, you told me that the groundwater is about 67% more than the surface water. So we have it more in abundance, more than the surface water. And for countries that don't have any surface water, any stream, then how does it survive? How could it survive? They have to go and explore the groundwater sources. Because no surface water. I don't know in Niger. Do you have any surface water? All the others is groundwater. But then, if you look at the figure, depending on, sometimes you may dig very deep to reach the good aquifer that will supply the needed amount of water. So for that reason, in Saudi Arabia, I know they can, here in Zaria we dig just 30 meters, and you have good amount of water that will keep on, but probably that is the unconfined aquifer. And there, like I said, for it to be sustainable and reliable, you need to dig up to confined aquifer. And that, when you hit a confined aquifer, you can be rest assured that in 100 years to come, nothing is going to happen to your well. Nothing. And that's why you may need to dig deeper more often than not. Because there you can dig a well up to 1,000 meters, 1,200 meters, 800 meters. And that means that will add to the cost. Because the deeper it is, the costlier it is to dig, isn't it? But in the long run, the more reliable that well is going to be. And even here, let's say in Maiduguri, you don't get water so close to the ground. I mean, you may have to dig sometimes 400 meters, 500 meters, borehole, because it is more or less a desert area. So the water level, although you can find probably water table from the unconfined aquifer, well, probably a few meters, but then if you really need a sustainable source, you may have to dig deeper. I don't know in Niger how many meters do you need to dig to get a good water? 200 meters. But then, when you have it, the water will be sustainable. You don't fear that one day it is going, it is going to be emptied. The water level is going to reduce. You can go and be rest assured that over so many years to come, you have no problem with the water source. But just because, our attitude here in Nigeria, more often than not, every house has borehole. Every house has borehole. And yet, even as it is, then you will find boreholes drying up. No way when you have confined aquifer. Because the water is inexhaustible. No. It is inexhaustible. But the only thing you need to have a clear demarcation of all the aquifers and what they are, so that you know the appropriate depth to drill. But once you do that, they can replace our surface water sources. And this is one of the untapped, probably, resources in Nigeria, groundwater. We still dig boreholes every now and then, but do we do the right one? We dig ones that after a year or two, they will dry up. They will not become functional anymore. It tells you that the planning and even our understanding, because most of us, I can tell you, let's say before this lecture, most of all, if I will ask you the same question, that can we use groundwater for municipal water supply, most of you, if not all, will tell me no. You will tell me that it is not reliable, isn't it? And that is because of the practical things on ground that we are seeing every now and then. Borehole drying up, isn't it? So you will tell me that no, it is not reliable. But I will tell you no. It is more reliable even more than the surface water. My time is up. I don't know what. Up till now, I didn't finish this.
Excuse me. There is a topic.
Maybe we will need more time. I don't know. We'll think about that. Probably these 3 hours is really short. And we have a lot of things. We have a lot to discuss. But don't consider this discussion as out of the lecture. No, it is an integral part of the lecture. Because it is a concept that if you have the wrong concept, that is what you will be advertising outside. All of you, some are lecturers, some are water practicing engineers in different companies, in different countries, isn't it? So if you don't have the correct concept, then there is problem. Okay?
Excuse me, I have a
Yes.
question. But then, where are other places like going into recharging groundwater?
Yeah.
Like, why do they have to recharge it?
Yeah, because this aquifer receives recharge. Without the recharge, over time, probably it may be depleted. Although, like I said, it has large aerial extent. But it needs to be recharged. Because recharge takes place for various reasons. It can be for water quality control. It can be to inject water to the aquifer so as to maintain the water level. Because even the confined aquifer has a source somewhere. Because that happens over time. We have what is called fossil water. So that they mine water as they do oil. It is called fossil water. Just like we have fossil oil or fossil energy or whatever. Because the water has been there for time immemorial. It is deep, deep, and deep down the ground. Just the same way they prospect oil, the same way they look for oil. And the oil, as we know, has been there for time immemorial, isn't it? The same thing with the water. It has been there for time immemorial. So once you have that aquifer, and the aquifers are well defined, they know exactly, okay, this is the Dammam aquifer, each aquifer has a name. So they know exactly, okay, in this town, it is underlain by so-so aquifer, so this aquifer is so-so meters beneath the earth's surface. So when I dig to this level, I will get this particular good aquifer. And then that's it. Pardon?
Would it also be that they are recharging the unconfined?
It depends. If we have a clear, if we have something as clear as this, so we know exactly where the outcrop is, so we can go and recharge it. Simple. It may appear as if it's unconfined, but it is the confined aquifer whose outcrop is at this area. My time is up. If you want to have another lecture, you can leave. This is just extra minutes, okay? Yes. I need to take attendance.
The fact that the groundwater is very charged, like surface water, in this in the desert countries, how does the groundwater get recharged?
It has an outcrop somewhere. There could be artificial recharge. And again, I just mentioned about fossil water, water that has been there for time immemorial. You know, due to this climate change, a lot of weather dynamics is changing globally. Where initially, a region where initially has a lot of water, a lot of rainfall, now it is experiencing drought. Who knows at the beginning of time whether even these deserts, were they originally deserts? Did you get my point? So this is water that has been there for time immemorial, in which we know that the weather keeps on changing every now and then due to now what we know as the climate change. So the water has been there for time immemorial, much the same way as the oil, because nobody went underground and planted the oil. But because of certain processes taking place over billions of years and then transforming into this, into that, you have oil, you have gas. Did you get the point? So I think, last question, and okay. Oh, okay, go ahead.
Just like to say, groundwater is very reliable. There is a local government in Katsina, Mali local government. Their major source of water is groundwater. They have 13 wells outside the town.
Okay.
Using this small generator set.
Okay.
They used to pump water to a ground tank.
Okay.
Now they use the tank, through the tank they now supply to a tank. Then they now supply
to individual houses.
That's what has been there.
So really, the more we understand that groundwater is even better to explore and more reliable and sustainable, the better for us, really. Although there could be concern, of depleting the aquifer over time. and also of degrading the water quality. Because like most especially in the desert, there is, I told you at the beginning about quality and quantity. Once you are pumping, you are indirectly deteriorating the water quality. The salinity of the water will increase. And even you can tell me that water in Nigeria probably it may be a bit saline. Because some of the deeper aquifers, most especially those surrounded by oceans and what have you. Because more often than not, in the groundwater, you can have, let's say there's an ocean here, and then this is the surface, this is an ocean. Okay? And then this is like the inland. There is a demarcation between the saline water and the fresh water. They don't mix. Why? Because of the density. Which one is heavier? Why is it heavier? It contains impurity. Must it be impurity?
It contains ions.
It contains ions, dissolved ions. It has more dissolved ions, calcium, magnesium, in such huge proportion, much more than the fresh water. So, if, let's assume your area is somewhere here and you dig a well, this is the fresh water source, okay? This is a fresh water source. But when you are withdrawing this boundary, the seawater, fresh water, the saline freshwater interface will be moving inland, inwards. Okay? It will be moving inwards. You are drawing water, the water level reducing, and then this boundary being pushed. Okay? Being pushed to the extent that, your water will now be saline. Do you understand? So pumping over time increases the salinity of the water. That's why even today most of the groundwater is really saline. It's saline, and that's why probably you will hear about sweet water. They have sweet water and raw water. The sweet water is the one you can drink. But the raw water is the one that is saline. You can do other things. You can bathe, but you cannot drink because the taste, you will feel as if, huge amount of salt has been stirred, and so you cannot, ingest. Of course, you can ingest. You can, let's say, make tea, but just to drink, as it is not palatable. Okay.
Sir,
Is it?
Sir, in the course of the lecture, you asked a question which you were not able to finalize it about the pressure, pluviometric surveys and mathematical expressions. So I want to tell you.
No, I will not tell you. This one, we'll go to it. We will go, but it's good you go and learn about what is pluviometric surface, mathematical expression. But we will go to a point where we'll discuss more about what is exactly the pluviometric head. So that's why I didn't push so much.
Okay, my first thing is in Saudi Arabia that they don't have there is no fresh water. Is it that the no surface water?
Yes.
Is it that the seawater is one that recharges their groundwater?
It could be, depending on the area, most especially coastal areas. Because this is like a coastal area, like Jeddah, like Dammam, like Jubail, they are all coastal areas. So their water will be more saline than the ones, that are far away from the ocean. But of course, over time, even if it's just withdrawing water from the aquifer, it makes it more saline. Maybe when we start discussing about the unsaturated surface, we will do some derivations here and there to see how the ions are increased over time. And once the ions increase over time, then it makes it more saline. Because there, it is very hot. So evaporation is high. So the water molecules are evaporated, leaving behind the ions. So they get concentrated over time. And that increases the salinity.
Let me answer the questions you asked, that he is asking. The pluviometric head, the mathematical formula is Z plus P
That's elevation and
Yeah, for now, we will defer that response. We hope you can recall it in our next class tomorrow.